So here we will consider a rigid body executing general plane motion. So general plane motion means, it is a motion where there is both translation and rotation. So suppose this is the rigid body which is executing a general plane motion. Now A is a point on the rigid body and G is the center of mass of the rigid body, and if we extend the line AG, then we extend it say up to point B, so that this AG is A and GB is B. Now what we want to do is we want to put a mass MA here and a mass MB here. Then how much this distance this B should be, how much this distance this B should be, such that this whole rigid body can be replaced by a massless link like this, where this is A, this is B, this is G, and there is a mass here, there is a mass here, which is MA, MB, this is A and this is B, and this is a massless rigid link. So the problem is like this. So this is a rigid body, and we take a point A on the rigid body, we extend AG where G is the center of mass. Then how much should we extend such that this distance is B, and we put a mass MA here and MB here. What should be MA, what should be MB, what should be B, such that this rigid body is completely equivalent to this two mass system. That means if we put a mass MA here, so A we know, small a we know, we do not know what is MA, what is MB and what is B. So the first condition for equivalence is the total mass needs to be same. So the mass placed here and the mass placed here, the sum of them should be the mass of the rigid body, and the center of the position of the center of mass should be preserved. That is, MA multiplied by A should be MB multiplied by B. So that ensures that the total mass is same and the center of mass is also at the same place. Now, so if total mass is same, this is the condition, and if the center of mass is preserved, then this is the condition. And now if you do this little manipulation, then you get MA as this and MB as this. But for general plane motion, the moment of inertia about the center of mass also has to be equal for this rigid body and this two mass system. So for that, what is the moment of inertia for this two mass system? That is MA into A square plus mb into b square, and that must be equal to m into kg square, where kg is the radius of gyration of this rigid body about its center of mass. Then again a little bit of manipulation, you put ma from here, you put it here, and this into a square this, so you get kg square is a b. So b is kg square by a. So if you know kg square and a, you can find out b. So in this way you can replace this two masses, this rigid body with distributed mass by a two mass system, one mass placed at this end and the other at this end. Now what is the objective of doing this? See, this is the connecting rod of a slider crank mechanism. So the length of the connecting rod is L and the center of mass is a distance away from the small end, and this connecting rod, for this connecting rod the mass is distributed. So if we put one concentrated mass here, then where should we put? Where should this point B be, so that we can put the other concentrated mass here? So this is Ma and this is Mb, and this we can determine from these relations. But what we want is to put the second mass not here but here at C, because if we do that, then we can replace this connecting rod with distributed mass by one mass here and the other mass here. Then what is the advantage? The advantage is this mass which is placed here will be executing a reciprocating motion along a line along with the piston, and the mass placed here will execute rotation about this axis along with the crank tip. So what we do here is, here we put the second mass at C. Here we put the second mass at C. So here the condition is Ma, but for equivalence actually we have to put the second mass here, and for that Ma and Mb we know, but that Ma and Mb we do not require. We want another set of Ma and Mc. So this Ma is not same as the previous Ma. This Ma is different, and Mb is not relevant here. Here it is Mc. So Ma plus Mc should be equal to M, and to preserve the position of the center of mass, this is the condition. So now this is Ma and this is Mc, and this is actually the moment of inertia. But this is not the true moment of inertia, because we know the true moment of inertia is m kg square. That means the true moment of inertia is actually m a b and not m a c. Because if we do this, then this is not the true moment of inertia about the center of mass. So we have to make some correction, and for that correction, so if the angular acceleration of this connecting rod is in this direction, and that is alpha, then the actual inertia force is MAB alpha in this direction. But if you take this as your moment of inertia, then the inertia force is MAC alpha. So to make this MAC alpha, MAB alpha, what you do is we give a correction torque of MAC alpha minus MAB alpha. So that means this MAC alpha, TC is MAC alpha, this neutralizes this this cancels, so these two cancel out and this remains in this direction. TC is in the direction of alpha. TC is in the direction of alpha and MAC alpha minus MAB alpha. So if you add it with this, then MAC alpha and this MAC alpha, they cancel out and MAB alpha remains. So this is the correction torque. So now you can put one mass at A, one mass at C, where C is, so this is C, this location is actually at the center of percussion, you must have noticed. But here for center of percussion, if you place the second mass at the center of percussion, then exact equivalence is maintained. But if here we are not putting it at the center of percussion, we are putting it at this point C, and due to that we are inviting some error in this inertia torque, and this is the correction torque also you have to give. So if you put one mass MA here, one mass MC here, then and you preserve the location of the center of mass, then MA is this, MC is this, and you have to apply a correction torque TC, where TC is this small l minus capital L, where capital L is A plus B. That means that is the actually center of percussion. If you suspend it from the small end, then this capital L is actually the distance of the center of percussion from the small end. So in this way you can get the equivalence. Here the advantage is, here since you put one mass at A and one mass at C, the mass placed at A is actually executing a motion along a line, a reciprocating motion along a line, and the mass placed at C is executing a rotation about the axis through this point.